So how does hello world look in memory? We're going to set the address here of our memory, and we're going to set the value here, and we'll be able to see it show up when we write it and when we read it. So let's start. H is ASCII value 104, which is 68 in hex, and in binary that is 011010000. So if we preview it, we can see that we have 011010000. That works for H. So let's write it by pressing this other button. So now it's stored in memory position 1, and we can check that by reading from the RAM. And we have 011010000. Let's write E, but first we need to increase our memory position, like incrementing a pointer. So now we're at memory position 2, and we can write E. So 011000101 is E, and we can write that to memory position 2. Let's look, make sure our H is still there, which is 68 in hex. So H is there, and then our E is there, 011000101. Now let's write L at position 3. Address now is set to position 3, which is 11 in binary. We can write our L, so 011011100 should be L. Check that. Write this to position 3. We can move on to address number 4. We need to write another L. That's pretty easy. It's still there. So we have two L's now, position 3 and 4. Let's raise this up to address position 5. We need to put in our O, 011011111, save to position 5. Now we need to add our comma. So let's increment our address pointer. So let's save this, increment our memory pointer. And now we need to add a space, hex for 20, which in binary just ends up being 001, and the rest are zeros. So that is space. We can save that. And then now we can move up our increment pointer, W, so that is 011, increment memory position. Now we need the value of O again. Now we need the value of R, so that's 0111. So we can save that. Increment our memory pointer again. Now we can put another L in there, so 011011100. Save, increment memory position. So we could see that this is exactly what a computer would be doing, except probably trillions of times faster than I'm doing it now. D is 011000100. Should be D. And then we can increment one more time, and we can put our exclamation point. So that's 0010000, and then there's just a 1 at the end. Should be exclamation. ASCII value 33. We can save that. And then at the end, we have to put a null terminator, so we can increment one more time so that our computer knows where the end of the string is if we were going to read this in a real scenario. So make sure that we have our zeros. We can write that. Make sure we save it. So now if we reset our memory and go back to the start, at position 1, we should have 0110100 for H. If we move up to position 2, we should have 011000101 for E. Position 3, we should have our L. Position 4 should be the same for L. Position 5 should be O, and in 4 ones, 001011100 is our comma. And then we have our space, 0010000. Position 8, we have W, which I think this is incorrect. This is reading O, so I think we skipped our W, or I overwrote it, showing how error prone this is compared to doing it with an actual computer. So let's just continue moving on. Position 9, we do have R, 01101110010, and we have L, turn on second bit here, which is 011011100. D, 011000100. Exclamation point is 0010001, hex for 21. And then we have our null terminator at the end. Should be all zeros. So we actually wrote out hello world, but it's cool to see. This is what's done trillions of times faster with a computer. Next, we're going to take this memory controller and integrate it with our 16-bit computer to have it read the instructions as it increments through the memory addresses automatically. So hopefully we can get that done, and it'll be really cool to see this working automatically without this manual input. So I'll see you soon, and thanks for watching.